Alright, so I'm turning on the YouTube stream right now, just so that I don't forget to do it later. It seems to be connecting right now, and I can see it now. So, live stream is on, screen share is on, and we are all ready to get started today. So the practice exam that I promised you that we'll be doing today is already posted in today's text channel. It is pinned right below the YouTube link. So if you go to the little bell thing, oh no, not the bell thing, it's the thumbtack thing. It would be the first item because I think it's reversed order. The most recent pin appears at the top. So just go to the pin and you can download the HTML document. Very good. So I found something about Joplin today. It was a very pleasant surprise. Joplin can easily accept a paste from a screenshot or a partial screenshot. Let me show you what I mean by that. So I'm gonna take a screenshot right now. I have a little shortcut key on my computer, and you can see all this too because I want to show you what I can do here. So I can just select any portion on the screen, and then with my screenshot tool I can copy just the clipboard. I don't even have to save it to a file. And then in Joplin, if I do a Control V, it will automatically, I guess it will upload the file first, and then you'll put a link to it. And this file is just kind of coded in a special way. I guess it's a UUID, and it's pretty cool. So the test is going to be next Thursday, and I believe that is November 4th. Let me go back to a browser and go to this class. Pretty sure I have this tab open already somewhere else, but what I'm trying to do is to set up the calendar inside Canvas, so this way we don't have to worry about not remembering when exam 2 is going to be. Alright, so let's take a look. This is October, and today is the 28th, so the 4th is going to be when the exam is going to be. So we'll schedule our exam 2 to be on November 4th, and the time, it's basically the usual time. It's from 9 a.m. to 10:20 a.m. Location is going to be online, just the same format as last time. And there we go. So now we have an entry in the calendar of this class for exam 2. Alright, cool. And then Richard asks, will exam 2 be like the first in which I send a Google Doc? Yes, that would be the same format. I will send you a document. Basically, it's a document that belongs to me, but I'm going to share that with you as an editor during the time of the exam, and then you're supposed to put in all of your answer, typed in everything during the time of the exam into that document, and then at about 10:20, depending on a few factors, but typically it is at 10:20 that I will start to run a script to unshare that document. So that's basically the same format as with the first exam. So any other questions about the format of the second exam? Because otherwise I can, go ahead and start to take a look at the practice test today. Jeff is asking a question. Will there be a practice exam? Let me see if I can find that tab because I got too many windows. I mean, I really don't want to be sarcastic, but that is in my nature. So if you guys go up to my post at about 8:02, that's the practice exam. Yeah. So I'm gonna have to pre-apologize for being sarcastic. Let me see. Where's my exam 2? Alright, so that tab is over here. But this is not the one that I'm looking for. Alright, fine. I'm just gonna re-download it and open it in a different tab. There we go. And then I'll put that tab over here. Alright, so this is the exact exam 2 for my summer session. And trust me, summer session for this class is crazy. If you think this class is kind of packed with material as a 16-week class, full semester, think about this class, with only half the time available. So it's basically the same thing as we do. Each class is 80 minutes, except instead of meeting twice a week, we were meeting 4 days a week from Monday to Thursday. So that was really pressed. Anyway. Basically the same thing. It is open book, open notes, no collaboration. In each person is supposed to work on his or her own exam. Okay, someone's mic is on. That might be Maddie. There we go. Okay, thank you. And write your answer in the document interleaved with the questions, because I don't want people to do everything on a piece of paper and then take a snapshot of the paper as a photograph and then turn that in. Also, whatever you need to turn in, you have to turn in the document that is going to be shared with you within the time that you are given. So, because I don't want people to send me an email and go like, well, I didn't have enough time to turn in stuff, so I'm going to send you my answers, through email. So I'm going to say that that is not going to work, okay? You have to plan your time accordingly. All right. So let's go ahead and start with question number 1. So question number 1 in this case is testing whether you know how to analyze the propagation of values within a circuit. And it's usually a circuit with some kind of a feedback mechanism. So all of the D flip-flops, all of the SR latch circuits that we have used, those are all circuits with a feedback mechanism. So they are kind of fun to analyze because of that. So the way we analyze this, we have done these steps quite a few times already, just maybe not with this specific circuit. And I typically would not name the circuit. In other words, this is a circuit to go through, but it may or may not be one of the circuits that we have talked about in the module, because the mechanism will still be the same. It's just that we have to follow the propagation of values based on whatever circuit you are given with during in exam 2. All right, so we are going to, so this is what I'm going to do. I am going to make use of the newfound power of Joplin. So I'm gonna copy and paste this into Joplin, so this way I can I can talk about the answer on the other side. All right, so let's switch to Joplin. There we go. And I'm gonna paste it here. This is for question number 1. Once again, you guys can focus on the right hand side when I'm working on the left hand side. Alright, so the first configuration with the input pins is A equals 1 and B equals 0. So we'll start with that. A equals 1, B equals 0. And we want to analyze how this circuit is, what this circuit is going to do. So there are two, basically we have to repeat two phases. Okay, the first phase is basically just to spread the value because of the node connections. Okay, so I'm gonna make it more detailed here. Okay, so node value spreading. Okay, so now we look at the connectivity of pin A with all of the other components. It connects to pin, the first input pin of P. So that means P dot in bracket 0 equals to 1. And I am going to use quotes here, because otherwise it will recognize the square bracket as a hyperlink, which it is not in this case. But you're only looking at the other side, so you should be fine. I mean, the syntax highlighting can be a little bit weird because it is not actually program code, but otherwise, it should still be okay. All right, so that's one, and then A also connects to the R pin of SR latch Y. Okay, so we'll say Y dot R also equals to 1, and and we can say because A equals to 1. Okay, because these are just the other things that are connected to the same node that A is connected to. So now we look at B. B is a lot easier. B only has one thing that it connects to, and that would be the reset pin of X. So X dot R equals to 0 because B equals to 0. So this is the easy part, okay? Because we are just looking at each node and find out, okay, we know this thing is changed or it is now specified. Where is it connected to? Because all of those other things connected to the same node would have the same value. All right, so now the next phase is to go through the components and find out what the components are going to do. All right, so we'll start with P, and then we ask the question, can we know what P is going to output? The answer is no. Okay, we cannot know what P is going to output because the second pin of P is connected to the output of Y, and you can assume all the SR latches have unknown states at the very first step of each question. So that means we don't really know what is the current state of Y. We don't know what is the current state of X. So we cannot know what is the output of P. So we can just say that P dot out is unknown. So this is after a propagational delay. So after propagational delay. So I'm going to just call it PD from now on. Alright, so P dot out is not going to be known, but on the other hand, if we look at X is also going to be, X is known, okay, after a certain propagational delay because B is a 0. So if B is a 0 and it is connected to the R pin of X, what do you think is going to be known about X? So this is a question directed to you guys because this is something that we have talked about when we talked about the SR latch. Ones as inputs is not going to be very helpful, but zeros as inputs usually would give us at least something. So if R is a 0, what would we know for sure about the output after a certain propagational delay? And Richard is typing something. And you also have to remember the SR latch is going to be based on the SR latch that we have talked about in our class. I have seen a lot of people using the SR latches from the internet that make use of the NOR gate instead of the NAND gate, and obviously answers derived from that Google lookup is all going to be wrong. So so you have to use the SR latches that are specific to our discussion in this specific class. Alright, so Richard said, I believe X would be unknown because X dot S is unknown. That is true. X dot S is unknown. However, because X dot R is a 0, we know one thing is for sure. What is going to be known for sure? Because if you kind of have to look into the SR latch with using two NAND gates, right? No. We know q is going to be a 1 for sure. Okay, so we know x dot q is going to be a 1. Now we have to explain it, okay, because now we have to explain it, due to the device, okay, because x is an SR latch and x dot r is a 0. Oh, I take it back. It is not. It's nq that is guaranteed to be a 1, not q. Sorry, that was my bad. There we go. All right. All right, so I'm just looking at the text channel. Jonathan is correct. NQ is 1, and I just fixed that error on my part. Well, there are two outputs, Matt. An SR latch has two outputs. You have to specify which one, and we cannot guarantee the other pin is going to be a 0. We just know that x.nq is going to be a 1 because we don't know what is the input pin S at this point. All right. Cool. Okay. So, and let's see. So p dot out is unknown because p dot in 0 is a 1, but p dot in 1 is unknown. And because this is a regular AND gate, so we just have one of the operands of an AND being true, but the other one is unknown, and as a result, the value or the value of the AND or the output of the AND gate is unknown at this point. All right, so that's a propagation, due to the type of devices that we are using. And then the other one, the one from A is connected to the R pin of Y, and that doesn't do us any good. Okay, that's no good coming from that, and that's why we don't say anything, because there's nothing that we can determine about Y. So now we are going to spread the signals. The only one that's worth spreading because of the node connection is x.nq. So now we do a node value spreading or propagation, or however you want to call that. So we have to look at things that we have just determined, which is x.nq, and find out how it is connected to other things. So you can change the way you phrase it. You can say because x.nq is now updated to a 1, then all the other components connected to this particular thing by a node would also be a 1. So we track it down. x.nq is here. It connects to y.s. Okay, then y.s is also going to be a 1 at this point, and that's the only thing we know, because x.nq only connects to y.s, and that's we cannot use the nodes to spread the values any further. All right, so Jonathan W. You don't have to say it, but you kind of have to remember that you got these phases that you need to work with, because we have to look at the nodes, spread the values, and then we have to go through propagation again. So the next step is going to be propagation. Okay, so this is going to be device value determination. Okay, because the input changes, because the input is now known, we can now determine the actual output of devices. So you can call it any way you want, okay, but I'm just going to abbreviate it and say after propagational delay. So what device is going to be affected? Well, this is the only new thing that we know about the circuit. Y.S is now a 1. So if y.S is a 1, and we already know y.R is also a 1, right? Because that was determined here. So we know y.R is a 1. Now we also know y.S is a 1. So both inputs of the SR latch Y are now determined. Unfortunately, we started off with an assumption that we do not know the state of SR latch Y. So now we can say, y.S, y.R is a 1, and y.S is also a 1, but y.Q and y.NQ are unknown, because at this point we cannot make any assumptions. And because of this, we are basically done because we cannot tell. We know for sure. One thing is for sure. Okay, one of them is a 0 and the other one is a 1, but we don't know which one is which one. Okay, and as a result, this is a dead end of change propagation, because beyond this point, we cannot we cannot be certain about anything. All right, so now we're moving on to the second transition. So this is going to take me a lot longer to explain than it would take you, to type the answer, because I'm trying to explain to you what I'm also expecting. So definitely you need to interleave between value determination because of just node connectivity, and also because of the device. So if it's because of the device, then it would take a propagational delay from the time that the input pin is determined to the time that the output pin may be determined, because in some cases, even after the propagational delay, the output cannot be determined because it's an SR latch with an unknown state in this particular case. All right, so yeah, as long as it is clear to me, Jonathan W., what you are indicating, it will still be okay with me. But it has to be clear. All right, so now we're moving on to the second step. Okay. Okay, I'm copying and pasting the image, just because when we scroll, it will be out of view and becomes difficult to see. So now we switch back to the question, which is in Firefox. There we go. All right, so Colton asks, what is propagational delay? Propagational delay is the amount of time that the output of a device it's the amount of time it takes for a device to respond to a change of its input pins. That's the propagational delay. Because nothing is going to be responding immediately. Even transistors has a certain delay. When you change the gate of a transistor, the change of flow, because remember, a transistor for us is really just a valve. It's either on or off. But from the time you change the value of the gate to the time the transistor actually allows or stops flow, there's a certain delay. So that's basically the most basic propagational delay is with a transistor. And then Dalton said, the time it takes for the gates to react to input. Yes, that is correct. Thank you. Jonathan W. is correct as well. And then Vlad said, if we have both inputs, why outputs are unknown. I am going to leave it up to you. I'm going to leave it up to you because that is the property of an SR latch. When both inputs are 1, the SR latch is simply saying, I'm maintaining my current state. So what if the current state is unknown to begin with? Then it is still unknown, isn't it? So a little bit of the studying for SR latch, would probably be helpful. Okay, so getting back to here, the next thing is A equals 0, B equals to 0. So when we get here, we only have to write B equals to 0 because that is the only change, okay? A is not changed, B is changed. So now we have to spread the change from what just got changed is, oh wait, A got changed, right? Okay, that was me, that was me, that was my bad. Okay, A got changed because A was a 1, now it is a 0. Okay, so A got changed. So because of node, okay, because of node connectivity, okay, well, we can abbreviate it as NC. We will also know a few other things would now be a 0. So now we know P dot in 0 is a 0, and we also know where's the other one, it's a Y dot R is also going to be a 0. So it is important to link, okay, these two are now known to be zeros because A got changed to 0. So it is important to have a because, therefore, that sort of thing. Just a connection word so that I can tell why these two are zeros. But that's because of node connectivity. So the next step is propagational delay, and after propagational delay, then we look at all the devices where one of their inputs got changed because A is now a 0. But that's just, okay, let's track down your device P and let's track down device Y because those are the two that got one of their input pins changed. So after propagational delay, then we are going to analyze the circuits that got at least one of its input pin changed. So we can just write down P and Y here for sure because those two just got at least one of its input pins changed. So we look at P and say, what do we know about P at this point? Well, we actually know that, we still don't, well, actually we do, yeah, we don't know about NQ from Y at this point, but we do know that, one of its input is a 0, and as a result we know P dot out is a 0 because P is a and P is an and gate, and at least one input is a 0. Alright, so that's good. What about Y? Well, Y, we actually know exactly what it's outputting now because we know that Y dot R is a 0, but from the analysis before, we also know Y dot S is a 1. So Y dot S is a 1, and as a result, Y dot, it is resetting, so NQ is going to be a 1, and Y dot Q is going to be a 0. So that is really important because now we got a few things that we have just determined. Okay, Y dot NQ is now determined, Y dot Q is now determined, and then P dot out is also now determined. So those are the three things, those are the three nodes, okay, that each one connects to a node. So now we have to find out, how those nodes are connecting to other things. So the NC analysis, the node connectivity analysis here, is going to start with that. Okay, so P dot out is 0. Okay, so we'll start each one to say because, okay, because we just determined these things. The next one is because Y dot NQ is a 1, and then the next one is because Y dot Q becomes a 0. So each one now, we are just looking at the nodes and find out where are they going. Okay, so I heard there are some questions in the text channel. Y dot NQ is a 1 with a question mark. Yes, it is. Because I'm not really sure what the question is, so I'm only going to confirm that yes, it is. And then Terence asked, do we still need to list that Y dot Q is even when it doesn't connect to anything after that? Well, I wouldn't know until I get back to the picture. So that's why this is here simply because I have made determinations up here. Now, if it doesn't connect to anything, that would be a pretty easy analysis because I would just say, okay, nothing happens after this, right? It still has a node. That node is basically trivial, okay? It doesn't connect to anything else. But I would still put it here just to be sure. Now, if you don't put it here and then you say because Y.Q does not connect to anything, okay, fine. Not a problem. Okay. Yes. Very good. Not offended. But that was not the intention because I look at the text channel and cannot determine what it is asking. There were nothing other than Y.NQ equals to 0 followed by a question mark. Alright, so P dot out is a 0, so now we have to find out what it connects to. Okay, it does connect to X dot S. So now we know X dot S is a 0. Y dot NQ connects to two things. It connects to one of the inputs of the P AND gate. So we know P dot in bracket 1 is a 1. It also connects to Z dot R. So now we say Z dot R is also known to be a 1 now. And over here, as Terence said, there's nothing else we need to say here. Okay, it does. There is no node. Okay, that's fine. Alright, so now we are getting back to the PD stage, because every single time after we have an NC, and then the NC, or the node connectivity analysis, indicates that we have just changed or determined one of the inputs to some of the components. Then we have to go through a propagational delay and then look at the devices that just got its input changed. So in this case, we know X potentially is one, P potentially is another one, and then Z potentially is another one. So these are the devices that we know maybe something got changed, maybe not. Okay, we don't know yet. Okay, so that's why we need to take a look here. Alright, so let's take a look at device X. Okay, device X has its input as follows. Okay, X dot S is a 0. Do we know what is X dot R? Yep, we know X dot R is also a 0 because X dot R connects directly to pin B, and that was determined earlier on too, because we know from early on X dot R is a 0 because B is 0 at that point, and B did not change, so it is still a 0. So as a result, okay, and then we say as a result, because X is an SR latch, now we know X dot Q is a 1, and X dot NQ is also going to be a 1. We look at device P, and we say P dot out continues to be 0. So no change here. So we don't have to go through the node connectivity analysis after this, because the output of P has not changed. Because P dot in bracket 0 is a 0. Because that connects to pin A, and pin A is maintaining a 0. It's an input pin. An input pin cannot change its value while we are going through the analysis of one particular input pin configuration. So P dot out continues to be a 0. So whatever P dot out connects to, we don't have to add those items to the list of things that we need to analyze any further, because P dot out did not change. What about Z? What do we know about Z at this point? So let's take a look. Okay, so let's take a look at the picture first. Z dot S connects to X dot Q, and I believe X dot Q has not been determined. And then we take a look at Z dot R. That's the one that we just determined. Z dot R is the only one that we just determined here. It is now a 1. So Z dot R, the output of Z is still unknown, because the only thing we know is Z dot R is a 1. And as I said, having an input being a 1 usually doesn't help with an SR latch. Having an input being a 0 is usually helpful. And that's one big difference between a NOR type SR latch and a NAND type SR latch. But in this class, we are using the NAND type SR latch, so that is kind of important. So now we go back to an NC stage, because we want to see if anything is now determined. The two things that are determined is X dot Q and X dot NQ, and we want to find out which one is a new thing to us. And I believe not both are new. One is already known before. Because B had been 0 the entire time, so we already knew that NQ is going to be a 1. Now we also know Q is a 1. So it really is helpful, okay, because right here we already knew that X dot NQ is a 1, and that is not changed. But N dot Q being a 1 is new to us. So when we look at the node connectivity, we now say, okay, we look at what X dot Q connects to. X dot Q connects to Z dot S. So now we say, because X dot Q is now a 1, Z dot S is also a 1. But that's it, okay? Because X dot NQ has been determined already before, so the analysis is already done before. It is not a change from what it was before. The only change, or the only thing that is new to us, is the determination of Z dot S. It is a 1 now. So we have one more PD, which does not seem to be very helpful. So the PD after a certain propagational delay, we now know that Z, the output of Z is still unknown because Z dot S is a 1 and Z dot R is also a 1. Z dot R is a 1 was determined earlier. That was determined when we know that Y dot NQ is a 1. Y dot NQ is a 1 was determined up here. So we already knew, that Z dot R is a 1. Now we also know Z dot S is a 1. But because Z as a SR latch started off with an unknown state, all we know at this point is we are maintaining that unknown state, and as a result, it is still unknown, and that would be the end of the analysis for this particular configuration of input pins. All right, any questions? Okay. So in the test, okay, you might find it helpful to copy the image a few times, and then you can start to annotate what you know about the nodes. What is a node change? A node change happens when one of the items or the only output item that is connected to a node is either determined or its state has changed. And then we have to figure out, okay, how is this node connected? How is this pin connected to other nodes, other pins, because of the node that it connects to? Is that okay, Colton? If you look at this NQ from X, this is the node. It connects to Y.S. So when we change, or when we determine the value of X.NQ for the first time, or when it changes, then we also know that it's going to change the input pin of Y, Y.S is going to change. And as a result, we need to track it because any change of input pins can potentially change the output of the device, where the input pin belongs to. So we have to kind of keep track of all of those things. Alrighty. Okay, sure. So now we are moving on to the third one, and once again I'm going to copy the image. You can do the same thing in the Google Doc. In the Google Doc, the image can be selected, and you can copy that. And better yet, you can also use Google Drawing. Okay, so you can copy the image and then insert a Google Drawing into the Google document, and then insert the image into the Google Drawing. Once it is inside the Google Drawing, you can start to use a text tool to annotate, these individual, nodes. So this way, it's easier for you to visualize, what you're tracking. Because otherwise, you're gonna have to scroll all the way back to find out, what the values are at this point, which is what I'm doing right now. All right, so I'm just giving you guys some tips about what you can do while you're using Google Doc. I'm not using Google Doc right now, so I have a little bit more restriction. So in this case, B is changed to a 1, so that would be the change. All right, so let's start the analysis. All right, so the change is B equals to 1, and this is going to be a node change analysis because B is just an input pin. So we say because B equals to 1, now we also know the following are also going to change to 1. So P dot in bracket 0 equals to 1, and we also know Y dot R equals to 1 because they are all connected to the same node, and that's why those things are changed. So in the propagational delay, after a certain propagational delay, the two devices that we need to pay attention to, one is going to be P, the other one is going to be Y. So now we have to look at P and ask ourselves, what do we know about the input pins of P? Okay, P dot in 0 is a 1, we know that, but just knowing one of the pins of an AND gate is a 1 is not really that helpful because now the value, the output of the AND gate is going to rely solely on the other input pin, which is, okay, we just track it down here. It is y dot nq. So now we have to go back and ask, okay, what is the previous value? What is the current determined value of y dot nq? And this is where, when you put the values in the picture, it becomes a whole lot easier to locate it, because otherwise you're going to have to scroll back, and we know it is a 1. So at this point we know, okay, so we kind of have to explain that too. P dot in 0 is a 1, and then P dot in 1 is also a 1, and as a result, P dot out is a 1 now. This is the first time. This is the first time we actually figure out, well, okay, not the first time we figure out what is P dot out, but this is the first time P dot out becomes a 1. Okay, and let's take, and this is a change. Okay, this is actually a change because it was a 0 before. Because P dot out continues to be a 0, that's what it was before, so it is changed to a 1. So I'm going to indicate this is a change just by using a word of changed here. Okay, changed here. So let's take a look at y, and we'll figure out what are the inputs of y. Y dot s is y dot. Okay, so we want to figure out what is y dot s at this point. Oh wait, no. Let's see. Y dot r is determined. Y dot s is the output of x dot nq. X dot nq is a 1, so y dot s is a 1. Y dot r we just determined is a 1, so the state of y, or the output, okay, I should make it more clear, the output pins of y are maintained. So when something is maintained, it means there's no propagation we need to worry about, because it means whatever it was, it still is. So there's no change propagation. However, because this one is changed, we have to kind of follow that and see what it's going to lead to. Okay, we got a few text items in the text channel. Alright, I'm confused about saying what we know, that we know P dot in 0 and Y dot R, because since they aren't connected. Or are you just saying we already knew those from the previous state? Yes, those are restating from what we knew before, because we need to know both input pins in order to make the determination of the output of the AND gate. Yep, okay, there we go. Next question is, I'm going to assume Y isn't B connected to X dot R. B is connected to X dot R. Yep. Or did I? Oh, I did mess up. Didn't I? Alright, so I could have messed up my analysis here. Let me double check. We have a change of B, so I think Ivan is right. Yep. Yep, so Ivan is right. B, because B equals to 1. B equals to 1 connects to X only. Okay, scrap this, and then we'll redo it from here. Thank you for pointing out that I missed something. Alright, so B equals to 1, and X dot R is now a 1. So when we look at the propagational delay step, the only thing that we need to look at would be X first. So now we need to, X dot R is a 1, we know that, and then X dot S is from before, so now we have to look up what is X dot S from before. Oh, okay, I see. Alright, so x dot s was a 0 and nothing has changed it, so it is still a 0. Alright, and then we say because x is an SR latch, now we know exactly what the outputs are because we know x dot, this is setting the output of x, so x dot q is going to be a 1 and x dot nq is going to be a 0. Now we look at these two and figure out which one has changed from before. So before, x dot q has already been a 1, so that's not going to be a change. But x dot nq was a 1 before, so this one is changed from before, so we have to follow this one. So now we have to go to another NC, node connectivity analysis, because x dot nq is now changed to a 1. We also want to see what else is connected to x dot q, and that one is not too bad. It's just z. So z dot s is also going to be a 0. And this is just because of these two belong to the same node. So when an output pin connected to a node is changed, then all the other input pins connected to the same node will change as well. And as a result, this is what we have changed. Okay, so I emphasize this is changed. And that's it. That's it for the node connectivity analysis. So after a certain propagational delay, whatever device has its input being changed, now we need to reanalyze that particular component, which is Z in this case. It is complex. Well, I wouldn't say it is complex. I think it is very tedious. Not so much it is complex. Shouldn't it be x dot q being a 0? X dot q being a 0. Nope. X dot q is a 1, x dot nq is a 0 because we are using a NAND type SR latch. In other words, if you want to set something, that thing, the set pin has to be a 0 in order to set the pin Q. If you want to reset something, that the R has to be a 0 to reset the Q pin.
Hold on. Can you hear me?
Yeah.
Yeah. So what I was trying to say was, because you stated that x dot nq equals 0, so z dot s is a 0.
Mm-hmm.
But the node that z dot s is
Oh,
connected to
right.
is the same one as x dot q. Yeah.
Okay, you're right. All right, so I made a mistake here because so this reasoning doesn't hold because NQ connects to something else. NQ connects to Y. Thank you, Richard. Alright, so this one is incorrect. So we're gonna change this one. It is still changed, okay, because we know that x dot q was a x dot nq was a 1 before, so it is still a change except it's changing a different pin. I followed the wrong wire. X dot nq is right here. It connects to y dot s. So Richard is correct. Y dot s is the one that got changed to a 0. And it is a change. So now in the next propagational delay, our focus is not going to be on Z. Instead, it is going to be on Y. And we want to know what the two input pins are. Y dot S is a 0. This is what we just changed. But what is Y dot R at this point? So now we have to go back and look at what is Y dot R. So Y dot R was determined up here. It was a 0, should still be a 0 at this point. And therefore, Y dot Q is a 1 and Y dot NQ is also going to be a 1. And y dot nq being a 1, we now have to, y dot q is not a problem because many of you pointed out before that it doesn't connect to anything. There's no node connected to it. So y dot nq becomes the only one that we kind of have to track, because if it has not changed, if it was a 1 before, then the analysis can stop here. On the other hand, if y dot nq was a 1 before, now we have to propagate that change because of the node connectivity. So now we're going to have to track down y dot nq, and let's see. So y dot nq was a 1, and let me just see if we have any further changes. Nope, so nothing has changed. So at this point we can stop this particular analysis. Alright, so moving on to the next stage. So the next stage is having both input pins being 1, so A is becoming a 1 in this particular stage. So we're gonna have a change of, so copy the picture first, and yeah, you can use no change. Yep. Alright, so now A is the one being changed. So because A equals 1, now we have to look through what A is connected to, and quite a few things. Well, two things. P dot in bracket 0 is going to be a 1, and okay, have to be careful this time. Y dot R is also going to be a 1. And now we have to look at the PD after propagational delay. Is P changing its output, and also is Y changing its output? So we're going to look at P first. We'll re-examine all the input pins of P. P0 just got changed to a 1, because of A being changed to a 1. So now we have to look at P in 1, and that should be determined somewhere before. If you know how to do a search in Google Doc, that's going to be helpful, okay? Especially if you can search backwards and you're documenting things in a consistent way. Let's see, P dot in 1 is a 1, was a 1, and nothing has changed it yet, because otherwise I would have seen something. Control F can do a reverse too. I think you can select the direction. Alright, so that is also a 1, and as a result P dot out is going to be a 1, and now we want to see if that is a change from before. I believe that is a change from before, but I will double check. So P dot out, we want to know what is the current P dot out, and P dot out was a 0 before, it is now changed to a 1. So we're going to have to indicate this is changed. And then we look at Y. So we look at both input pins of Y, Y dot S is was a 0. Okay, that's from right here. And then Y dot R is now a 1. And because Y is an SR latch, so that's why Y dot Q is going to be a 1, and Y dot NQ is going to be a 0 in this case. So now we have to look at Y dot Q and Y dot NQ and see which one has been changed, if any. Y dot Q was a 1 from before, Y dot NQ was also a 1 from before, and that was not a change, but Y dot NQ being a 0 is changed. So this is the important step, okay? We identify everything that has been changed after propagational delay. So when we look at the node connectivity, we basically pick those things up and say because those things have changed. Because P dot out is now a 1. It was a change from what it was before. So now we have to look at everything else that connected to the same node that P dot out is connected to, and and we'll also say because Y dot NQ is changed from a 1 to a 0. Now we have to look at everything else that connect to the same node. All right. So because P dot out is now a 1, it goes to X dot S. And that's the only thing it connects to. And then Y dot NQ finally connects to something in Z. It connects to the R pin of Z. So Z dot R is now a 0. So for each one, we also have to look at, okay, is that a change? So X dot S, we have to look at the current state before this. of x dot s and see whether it was a 1 or a 0. It was a 0 before, it is now changed to a 1. So we say this is changed. And then we look at z dot r and find out whether it was a 0 or a 1 before. If it was a 1, then it is a change. If it was a 0 already before, then it is not a change. I believe it was a 1 before. P dot in 1 is a 0 because y dot nq. Y dot nq. Oh, that's one more place to go to. Okay, so and P dot in 1 is also a 0. Thank you. Alright, so the question is that a change? And because we know this is a change, so we know for sure this is going to be a changed state as well. And so is this one. Because when an output pin change, then all the other input pins are going to be changed as well. So now we look at PD, and we got 3 devices to look at. We got X, we got Z, and we also got P again. So this is the tricky part, because within the same pin configuration, because all of these analyses here, they belong to the same pin analysis. But within the same pin analysis, one particular device can have a change within, because of the propagation of changes, it can change, within that too. So now we look at X first and see what it is. Yep, we're still on number 1. But remember, I'm not labeling the nodes, and that's adding to the difficulty of the analysis. You can always put this into LogicSim. Now, let me kind of digress a little bit first. Okay, you can put this into LogicSim. There are 2 things you have to be very careful about when you put this into LogicSim. One is LogicSim does have a SR, they call it an SR flip-flop, but it's not a, they don't call it a latch, okay? So you might want to create your own SR latch out of what we have talked about in this class using 2 NAND gates, because that will make sure that you're using the correct kind of SR latch. So that's the first thing. The second thing is LogicSim is very, very good with giving you the final output of the pins, of all the outputs of the components, but it's not very good at explaining how the changes propagate, which is what I'm going to use for grading purposes. So you can use LogicSim as a kind of like a final check to see if the final state of the analysis is right or not. You can do that, okay? But it's not a very useful mechanism for explaining why things are in a particular way. So, yes, you are allowed to use LogicSim. I mean, it would take me a lot of work to say that you cannot use LogicSim, so might as well just let you guys use LogicSim. But what I'm looking in the answer is not something that can be directly answered because of the use of LogicSim. So I just want to make sure that people are aware of that. Alright, so moving on, but I'm not using LogicSim at all, so that makes the analysis a little bit difficult. The nice thing about LogicSim, even if I don't turn on simulation, is when I poke on a particular node, it highlights the entire thing, so it becomes easier for me to kind of track down what it is connected to, and I won't make as many mistakes as I just did in this analysis here of, kind of following the wrong wire to the wrong component or forgetting one of the components. So if you use LogicSim, at least that part would be easier. Exactly. So what I'm looking for is exactly what Richard has typed in the text channel. I'm looking for your understanding of the circuitry and how to analyze the circuitry. I'm not looking for whether you can input this into LogicSim and copy the result from LogicSim. That is not what I'm testing. I'm testing whether you can perform the analysis and explain it to me. So Richard is 100% correct about that. Alright, so getting back to the propagational delay. So after a propagational delay for every device that we want to track down, you have to look at all the input pins and then determine whether the output pins have changed or not. So we have to look at x.s. Alright, so x.s is just determined to be a 1. x.r on the other hand was determined earlier. And then I have to look for it, but if you have been using the diagram to track all these stuff, then you wouldn't have to spend as much time. x.r is a 1. So and then we say because x is an SR latch, its output are maintained. So in other words, no change here, okay? Just because x.s is changed from 0 to 1, the outputs of SR latch x did not change at all. So that would be a dead end, okay? In terms of the analysis, that's going to be a dead end. So now we track down z.s. So z.s was determined earlier, and I'm going to have to scroll back. So z.s was a 1 before, it is still a 1 at this point. And then z.r got changed, it is now a 0. So now we say because z is an SR latch, z dot, this is a reset operation, so z dot q is going to be a 0, and z dot nq is going to be a 1. Okay, so next one is p. Alright, so for the AND gate P, we want to look at both input pins. Input pin 0 is connected to A, and that is a 1. P dot in 1, we just determined that because we just changed it, and it is now a 1 as well. So P dot out is now a 1. Okay, and then we say because P is an AND gate, P dot out is now a 1, and now we want to find out whether that was a change or not, and I'm pretty sure it is a change, because if P dot in, let's see here. Oh, right, because here, because it was a 1 before, and now it's a 0, so that is P dot out is definitely a change to a 1 because it has to be a 0 from before. Wait, hold on a second. Okay, P dot in is a 0, it is changed. So I am incorrect here because I just copied it wrong. There we go. It is a 0, so P dot out is a 0. Okay, there we go. So I just made a mistake. Alright. And P dot out being a 1 is a change from before, so now it is changed again. Z is not changed. Let's see. It is a change. Z dot Q is now a 0. Z dot NQ is now a 1. I believe the Q and NQ of Z was never determined until now. So they were all unknown, and now they're known. Okay, yep. So these are both changes. So we note these are changed. This is changed. And this one is changed as well. Alright, so that means in the next stage, which is the NC, the node connectivity analysis, now we have to track down what Z.Q connects to. That's an easy one, because Z.Q is now a 0, C is now a 0. C is the output pin. And then the next one is also going to be this easy one because NQ is now a 1, D is now a 1. Pretty easy. The more tricky one is going to be P. Okay, so we say because P dot out is now a 0, we need to track down, it goes to X dot S. Okay, X dot S is also going to be a 0. And this is a change, okay, because P dot out was a 1 before, and now it is a 0. So now in the next PD, we have one device to track. Okay, C and D are output pins, so they don't go anywhere, and there's nothing to track with C and D. But X, on the other hand, needs to be tracked. So we say X dot S is a 0 and X dot R is a. Let's take a look. X dot R was a 1, so it is still a 1 at this point. And X is an SR latch. So now we know it is a set operation. So X dot Q is a 1 and X dot NQ is going to be a 0. Now we want to find out which one of these two, or if any, is changed from what it was before. So we need to look at Z dot Q and Z dot NQ from before. So this one is not helpful because it is a no change from before. So we have to go further back to find out what were the outputs of X. So X dot Q was a 1, X dot NQ was a 0, and X dot Q is a 1, X dot NQ is a 0. So we're gonna say no change, which is good, okay, because that means we are done with this particular step. All right. So the next step is going to be about the same thing. Okay, so I might as well finish the whole thing because at this point the change is B is getting a 0. So we go back here and copy and paste the picture. And then we say B is now a 0. And because this is an NC, everything starts with an NC to begin with. And then we say because B is now a 0, we also determine that X dot R is going to be a 0. X dot R is going to be a 0. So now we go to a PD. Because P was a 1, because B was a 1 before, X dot R being a 0 is going to be a changed state for sure. Because if an input pin is not changed, I don't even bother to mention it. So now we have to look at a propagational delay effect, and we look at both inputs of X. So X dot S is something, and X dot R is going to be something. Alright, so we look up from before. X dot S was a 0. Okay. X dot R was a 1, but now it is a 0. And because X is an SR latch, both outputs are going to be 1s at this point. So we got X dot Q being a 1 and X dot NQ also being a 1. But we have to find out which one is changed. This one is easy because we just determined that. X dot Q being a 1 is actually just maintained, no change there. X dot NQ was a 0 before, and this one is changed. So we have one more, at least one more NC, because X dot NQ is a 1, whereas it was a 0 before. So now we have to look at all the input pins that X dot NQ connects to via a node, and that is just one single one, which is Y dot S. So we say Y dot S is a 1, and that for sure is going to be a change because Y dot S was a 0 before. And then we go through another PD. This time we have to look at the Y device. So Y dot S is a 1. Y dot R. Okay, there's a text message. Well, I think we got about 15 minutes left. I can always shorten and make have one fewer transition. But remember, I'm also going through this without using the use of Logisim, and you guys can use Logisim. It will take you a little bit of time to enter the circuit, not really that much. But with Logisim and also with annotation on the diagram itself, that makes the search of the existing value of, for instance, Y.R here, it makes it so much faster because right now I have to visually scan through my own text to find out what was the previous state of Y.R. But if you already have it annotated in the picture, it really makes it a whole lot easier. Um, we got two more. All right, so okay, y dot s. Wait, y dot r. I need to find out what is the value of y dot r. So if you have a systematic way of tracking all of these things, like in the picture itself, it really does make a huge difference because now I have to go back. Or if you know how to use a search feature, I'm not sure whether search works here. Oh, it does. Nice. But I think it only goes. It does go in the opposite direction too. Okay, let's try to use this feature. Y dot r equals 2. And at least it highlights everything. Oh, if I knew about this, right? I mean, all right. Tag in tools, yes. So y.r is a 1, was a 1 before. We already know that. So now we have to say because y is an SR latch, its outputs are maintained. In other words, no changes whatsoever. And that's basically it. Okay, this is the end of the analysis because we just have to reach a no change for everything that we are trying to track. Then we are done. All right, so I'm going back to the text channel. Lab today. Well, maybe. We have three to answer. Yes, two more. I will simply stop time and finish the exam. Yes, you go ahead and do that. All right, so this is for question number 1. But as I said, if you use the tool, to track the current state of the nodes, more conveniently, the analysis it can go a whole lot faster. All right, so question number 2, is giving you a bunch of states for the tunnels coming out of the processor. So with this one, you can also use Logisim to help you. You can bring up the processor itself, okay? But it's much harder to kind of inject these values into those specific tunnels. So in other words, you still have to kind of manually analyze the processor circuit in order to find out what this is going to do. It has some subparts to the question. Go faster. All right, so and also using Logisim, you can also double check the end of one particular stage. So that helps a lot too. If you make a mistake, you can basically spot it within one particular stage and not let that mistake continue to propagate to the next stage. So that makes a difference. Are the values in question 2 in decimal or hexadecimal? These are all, well, nothing is going to reach the point where it does make a difference. So you can look at these as decimal or hexadecimal. It doesn't really make a difference because the largest value we can specify on one of these values is 7. PC Mux Mux can go from 0 to 7, and 7 is 7 whether it is decimal or hexadecimal. So it really doesn't make a difference in this case. But if you want to know exactly what they're meant to be, they're meant to be base 10. All right. So the first one is to identify the components that are going to be updated is /r because it may be a single component, it may be multiple components. So now you have to go to the circuit and find out what is going to be updated. So the way I just visually analyze this is to look at the RAM cell. RAM cell is a 1, which means RAM is being selected, which automatically asks the question, what is RAM load? RAM load is also a 1, which means we are reading from RAM, so RAM is not going to be updated. That is, so we can rule that out. Pin 0 out of the D pin of ROM connects to, I think it's the instruction register. So in this case, the instruction register is going to be updated. So IRReg or instruction register should be a part of the first part of the answers. RI mux is a 1. That itself doesn't really tell us anything, but because RIEN is a 0, so we know none of the registers inside the register bank is going to be updated. So if you want to ask the question of, but how do we know that? Why do we know that when RIEN is a 0 that none of the registers in the register bank is going to be updated? you have to look at the register bank itself, okay, and find out how the RIEM pin is connected to the it is like a demultiplexer, except the input is always of 1. What is the name of that thing? Decoder, that's right. So because the decoder is turned off, so that means none of the enable of registers A, B, C, or D can be a 1, which also means registers A, B, C, and D cannot be updated. So we go further down. PCEN is a 1. Okay, so that means the program counter is going to be updated. So in this very specific case, the program counter is going to be updated. The instruction register is also going to be updated. Those are the two components being updated. The next part of the question is asking how these components are updated. For each component that is updated, identify how it is updated, and explain why you think this is how it's going to be updated. So you want to look at the multiplexers, demultiplexers, and so on to explain how the paths are set up. Now, this part of the question, the second part, I can't answer without bringing up LogicSim, because I cannot remember all the different multiplexers and demultiplexers, which value specifies which path. So you're going to have to use LogicSim, bring up the processor, which I am going to do right now. There you go. Alright, so let's continue this analysis. We know that the instruction register, which is this one here, okay, let me change to this tool. So we know the program counter is going to be updated. We also know the instruction register is also going to be updated. The question is, how are they updated? So now we have to track down the input to the program counter. So the program counter, so you have to look at all of these things here. Okay, so you might want to have your LogicSim to be able to display side by side, so this way it's easier to read. The program counter connects, okay, change to the poke mode because this will highlight the actual node itself. So it connects to this multiplexer, which is controlled by PC mux mux, and we talked about how PC mux mux in return is controlled by PC mux is determined by PC mux mux in this case. So we look at PC mux mux, it is a 1. So if PC mux mux is a 1, it's taking input 1, which is, let's see, CZ. It is using the Z flag to determine PC mux itself. And so it depends on the Z flag. And then after that, we also want to right. So we also want to, so PC is updated depending on the Z flag. If the Z flag is a 1, then PC mux is going to be a 1, which means it's going to go through this node over here. So we have to kind of follow this node too and assume that PC mux is a 1. If PC mux is a 1, RI register output enable is the other pin that connects the output of this NAND gate, AND gate. Sorry, this is just a regular AND gate. So we have to look at register output 0 enable. Register 0 output enable. Register output 0 enable is a 0. Okay, so this is a 0, but since it's negated before we connect to the AND gate, so the output of this AND gate is going to be a 1, which means this is the input that will feed to the output of this multiplexer, and this one does connect to the D port of RAM. So that means if the Z flag is a 1, we are reading whatever is in RAM that is being addressed at that time in order to update the program counter. and also the instruction register, because you can see how the instruction register is also directly connected to the D port of RAM. So both registers will be updated by whatever content that the RAM is addressing at that point. So now the next question is, what is determining the address of RAM? So now we have to track down the A port of RAM, and the first thing we need to figure out is what is ADDR mux, address mux. And oops, you have to look at the question again. Where's the question? Right, there you go. So we have to look at ADDR mux. It is a 1. So going back to the circuitry, we say that if this is a 1, then we are using input 1 to connect to the output, and that is coming out of the program counter. So now to answer this question, okay, to answer part 2 of this question in Joplin, okay, this is for question number 2. So the first part is the program counter and the instruction register will be updated. And then for part 2, I'm abbreviating. I'm not repeating what I said about the reasoning of how I know this. So what we know is both the program counter and the instruction register, well, the program counter for sure is going to be updated in this way. It's updated depending on the Z flag, because the Z flag is bit 1 of the flags register. If the Z flag is a 1, then we are just using whatever the program counter is pointing to update it. And I'm going to use 3 backticks here, so we know this is just your regular code. There we go. And if the Z flag is a 0, it will just auto increment, so it will just be PC plus 1 in that case. On the other hand, the instruction register, you can spell out the whole thing. Instruction register is just going to get whatever the program counter is pointing to, because that one is not conditional. It is connected directly to the D port of RAM. So this is for the second part. Okay, now we move on to the third part of the question. The third part of the question, there are 4 parts to this. But once you get to the third part, the fourth part is really easy too. We got this one. Alright, does this microcode slice remind you of an existing instruction? Okay, so we look at the effect of the instruction here, and you can use the opcode table to help you. So if you use the opcode table, other than this, okay, we kind of recognize this. And because that's something that we just talked about on Tuesday. So we look at this and go like, oh, that looks like JZI, okay? But let's make sure that this the question is asking about the mnemonic. Okay, determine the exact and specific mnemonic of this instruction. Okay, so that is JZI in this case, because that's the closest that we can get. And then the next one is asking you about the hexadecimal opcode, and that you also can use the opcode table. So if I look up the opcode table, I got the tabs spread all over the place. So opcode table is, I have a tool, I have a Firefox extension that can resume all of my tabs, but sometimes it doesn't get it to the right window. That is the problem. So in this case, JZI is right here. It has an opcode of 45. So getting back to Joplin, the opcode is 45 in hexadecimal. So this is a good time to double check to see what is the format that I'm expecting. And it does ask about hexadecimal. So it is just 45. There we go. Alright, so I think I heard a ding from Discord. I can make the first question a little bit shorter, or anything that resembles the first question to be shorter. So that way, instead of 5 stages, I can make it like 3 stage or something along that line. Uh, Alrighty. Well, it's not going to be like the first exam because these questions are not like each other. So I'm not asking the same kind of question. All three questions are of different kinds. So I can assume I can make these a little bit shorter. So instead of having 5 steps here, maybe fewer steps. But I'm not going to promise anything. I learned not to promise anything. But I'll take your input into consideration, as they say. Yes. Okay. So getting to question number 3. Well, I am explaining at the same, along the way, and I did not even use, the search feature in Joplin to help me locate the value of a previous thing. So, that really helps to kind of, it really makes it a lot longer. All right, question number 3. Yes, I understand what you guys are saying. But the whole class, basically have the same kind of questions. So at least it is fair. I'm not giving some people some difficult questions and other people easier questions. That's for sure. I would never do that. Okay, so question number 3. Let's start with the value in base 10 as a fraction is 327 divided by 4. The first part of the question is to figure out how this value is represented as close as possible as an incorrect double precision floating point number. Compared to the correct format, this incorrect format has the exponent taking up 3 bits with a bias of 63. Because of this error, the fractional Mantissa has 56 bits. Using the following space, show the conversion of value v, which is this 327 divided by 4, into the erroneous floating point number bit pattern step by step. I need to know that you know the general floating point number format, correct width for the width field or not, and know how to convert, meaning that just stating the final answer will earn 0 points. Show the bit pattern in hexadecimal. Alright, so getting back to the text channel, I'm not going to answer any questions related to, this is too long, I cannot finish it, because I would like to finish question number 3. So anything unrelated to question number 3, I would defer the answering of those questions. No, the summer 2021 was worse. Simply because the time is far more compressed, and many people in the class could not, in one way or another, I cannot understand. I don't understand the reasons, but I think a lot of people could not keep up because it was way too compressed. So instead of having, 1 week to absorb, the material of 2 lectures, they have 1 week to absorb the material of 4 lectures. So it is, the amount of time was just cut in half. Well, this is a difficult class. This is not by any means a easy class. It is one of those quote unquote divide, in a major. Alright, so getting to question number 3. So let's find out what question 3 is really asking. Okay, so we want to convert this value into, so let's just say there's no lab today. I'm going to use today's lab to finish this entire thing. Yay! Okay, so I do want to respond to Maddie's comment. Alright, so there's a curve, okay, to become a competent and successful developer or computer scientist, or someone who you want to be, because, otherwise you wouldn't be taking this class, right? You wouldn't be trying to pursue a degree in computer science. So there's a certain level of competency, a certain level of ability, in order to succeed in this field. To get to that point, okay, you can look at, imagine a curve, okay, to get to that point. So the way I do things is to put the steep part of the curve early on. and instead of putting it later on. Why is the mantissa in the format of x divided by y? Oh, that's easy, because this makes it easy to do the conversion. Well, also I can make variations of this question, more easily using this format. But let's go ahead and take a look at this value, 327 divided by 4. Okay, so I'm switching to Joplin at this point, and this is for question number 3. So once again, you guys can focus on the right hand side when I'm working on the left hand side. Alright, so this is going to be a math equation thing, so I'm going to use $. I think it can handle multiple lines of math equations when I use $. We'll see. So the value we are dealing with is 327 divided by 4. Okay, and then we want to see how we can re-express this. And I think backslash opens up a new line. There we go. And I'm not sure whether I can use a ampersand so it spaces out correctly. Nope, doesn't seem to like that. I'm trying to format this, so that we can express the same thing on multiple lines, and it doesn't seem to like that. Alright, fine. We'll do it the other way. Alright, so we're gonna do it just using the usual way. Okay, so we want to convert this into a binary format first. So 327 divided by 4. We look at 327 and we say, okay, it's 256. Now, obviously, you guys can use a calculator. Okay, you can use a calculator to do all of this stuff here. I'm just going to go through this using just mental math. And 327 subtract 256 is going to give us a 171. So we have a 64. 71 minus 64 is 7. So 7 has a 4 plus 2 plus 1. Okay, and the whole thing divided by 4. Don't forget that. Alright, so now we're going to look at this and convert it into a binary number at this point. Yes, binary stuff. But a lot of calculators can help you convert base 10 to base 2. If not, you can use a spreadsheet. Just use Google Sheet. Google Sheet has, I think it's called DEC to bin, DEC to BIN. That will convert a base 10 number into a binary representation right there for you. So you could use that. I just wanted to use mental math to do this because I'm too lazy to bring up a spreadsheet. But I now have to go through the math here and make sure that it looks right. Yeah, it does look right to me. Alright, so 256 is 1 followed by 10 zeros. I mean 8 zeros, sorry. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And we know these 3 are going to be 1s, and then we just have to identify the 64, which also needs to be a 1. So we have the 256, 128, and the next one is a 1 here. That should be the 64. Now, we can double check because 64 is 2 to the power of 6, which means in binary it's going to be a 1 followed by 6 zeros, so 6 digits. 1, 2, 3, 4, 5, 6. So I think we got that part right. So this is a base 2 number. Okay, I'm going to use a subscript of 2 to indicate this is in base 2. And we have to divide it by 4, which means we can multiply that by 2 to the power of negative 2. So I'm going to do that. Times 2 to the power of negative 2. There we go. Alright. Is dividing before the same as bit shifting right 2 times? Yes, it is effectively the same thing. Alright, so now we have the value specified as a binary number with a binary with a base 2 exponent. So we are pretty close to what we need at this point because we just have to re-express everything into 1.010000111 in base 2, but we have to adjust the exponent of 2 because we just did a whole bunch of right shifting on the mantissa, and the number of times we do the right shifting is the number of times we have to add to the exponent of 2. So how many times did we shift? Let's do some counting here. 1, 2, 3, 4, 5, 6, 7, 8. So we have to add 8 to the exponent of 2. So that means we have 2 to the power of 6 at this point. So everything up to this point is just algebra. Okay, this is like really, really basic math. So now we look at this and go like, okay, so we have all the basic stuff that we need to come up with the binary bit pattern for this particular number. Specifically, we know E2, which is the exponent in base 2, is 6 in this case, which means the biased exponent is going to be 6 plus whatever the bias amount is. Okay, and according to the question, because I made a mistake of understanding a double representation, the bias is not 1023 and instead it is just 63. So it is 6 plus 63, which is what? 69, right? And 69 is 64 plus 4 plus 1. So that means in binary, this is going to be 1 followed by 6 zeros, 1, 2, 3, 4, 5, 6. And then the least significant bit is going to be a 1 to account for 2 to the power of 0. And then 2 to the power of 2 is also going to be a 1. So that would be this one over here. So this is in base 2. All right, and then the fractional mantissa is whatever is to the right-hand side of the point. So we are talking about just this portion here, excluding the point. Okay, so let's see if I can select just that portion. All right, so it would be this, followed by a bunch of zeros like that. So when we put the whole thing together, the value itself is non-negative, so the sign bit is going to be a 0. So sign bit is a 0. So when we put this together as a base 2 number, okay, I'm going to use, well, actually I can use, I think it's 5 spaces. Okay, I can make a block with 5 spaces at the beginning, and it turns into just a pre-formatted style in HTML. 1, 2, 3, 4, 5. There we go. And now I can specify this as a 0 followed by, let me see, how many bits did I allocate to the exponent of 2 in the erroneous way? 7 bits. Okay, so we have 7 bits for that, which is exactly this. Okay, this has exactly 7 bits, so we just copy and paste the 7 bits into here, and then we have the fractional part of the mantissa, which is just this portion here. So this is just a concatenation of everything that we have figured out earlier. And because the answers, the question specifies that I want the hexadecimal representation, so now we have to break it up. Okay, so we have 0, 1, 0, 0 as one chunk. Okay, the best way to do this is not to visually line up everything because that's going to be prone to error. So the best way to do it is to, this is how I would do it. You guys can choose however you want to do it, but I would just kind of make it into one big chunk and then break it up into chunks of 4 until we get to a whole bunch of zeros. So now we have 4, 5, and then we have 4 again, and then a 7, and then a bunch of zeros. So in hexadecimal, this is 4, 5, 4, 7, and then the rest are our zeros. But we need to know how many zeros we need. There are 16 digits. We need 16 digits to make up for 64 bits because one hexadecimal digit is 4 bits. So we have 4 already accounted for. That means we need 12 zeros after this. So we just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. So this would answer the second part of this question. Oh, the first part, sorry. The first part of the question. The second part of the question is, given the incorrect bit pattern is interpreted by the computer using the correct IEEE double precision floating point number format, what is the actual value being represented using this interpretation? Alright, so what that means is I'm going to take these 64 bits, but this time I'm going to interpret it correctly using the right IEEE double precision floating point number. The bias of 63, okay, that's it's the constant that you add to the actual exponent of 2 when you want to represent the exponent in a double in any type of IEEE floating point number representation. So the correct bias is 1023, and the correct number of bits to allocate to the exponent is 11 bits. So I made the mistake intentionally here to only use 7 bits for the biased exponent, and the bias amount is 63. So it's really just me making a mistake intentionally to see if you guys can kind of identify the various components of a double precision floating point number. Now, during the test, okay, you can use Google and look up what is the proper double precision floating point number format. Wikipedia makes a great entry for this because it actually has a picture and shows you, hey, this bunch of bits over here is the fractional mantissa, this bunch of bits here is the biased exponent, and this one single bit standing out all the way to the left hand side is the sign bit. So you can look up Wikipedia, you can pre-look up Wikipedia because we know at least one question is going to be on double precision floating point numbers. So you can pre-look up all of that stuff, line up all your tools, so when you are in the exam, you don't have to look up those information during the exam. All right, so now we take a look at this and we break it up back into the bit patterns. But this time, okay, we're gonna take a look. So we're gonna reuse this, okay, down here, and this time we separate the sign bit. So this is the sign bit, and then we have the exponent being the 11 bits. Okay, now how do we know it is exactly 11 bits? Because IEEE says so. Okay, so these would be our exponent bits. And then what is left would be our fractional mantissa. So the fractional mantissa would just be 0, 1, 1, 1 followed by a whole bunch of zeros. Okay, so that's just that part. Alright, so now we look at this, and now we say the value being represented is, we know it's non-negative because the sign bit is a 0. So the next thing we want to know is, what is the mantissa? The mantissa is going to be 1.0111 in base 2. And then the actual exponent in this case is going to be 2 to the power of, I'm using, well, might as well use the math notation here. So the exponent actually looks like exponent, right? Alright, so now we are looking at the actual math equation, but we have to use braces instead of parentheses for this. There we go. Alright, so in base 2, we have 1, 0, 0, 1, 0, 1, 0, 1, 0, 0 in base 2. But we also know the correct bias is 1023, so we have to remember to subtract 1023, which is base 10, from whatever this base 2 number turns out to be, using the unsigned interpretation. And obviously I don't really want to use asterisk here. It just doesn't look right. There we go. So now we look at this, and then we just try to work this out. 1.0111 is 1 plus 0.25, which is the 0.01, and then plus 1/2 of that, which is 0.125, plus, and the 1/2 of that is, if I remember correctly, is 0.0625. That would be that would these are all base 10 numbers, accounting for just the mantissa part, and then we want to multiply this by 2 to the power of. Okay, so now we have to figure out what power of 2 we are dealing with here. We got 1024, which is what this one here is representing, and then we got some ones kind of sprinkled throughout this whole thing. Alright, so I'm just going to be counting this one, followed by how many zeros. This one is followed by 6 digits in base 2, so that's a 64. And then the next one up is, we skip 32, and then we have 16, and then we skip 8, we got 4. There we go. And then we have to remember to subtract 1023 from that sum. Alright. I mean, I think you guys are really kind of getting the idea of how this calculation is going to be done. So now we just say, what is that? I mean, at this point, just use a calculator, use a spreadsheet or whatever to do to finish up the whole thing. Yeah, you can use a binary to decimal converter. In a spreadsheet, it's called bin to dec. BIN, and then the letter 2, not letter, the digit 2, and then dec, DEC. There you go. Alright, so Matt looked up Wikipedia. Yep. I believe that is also linked from my modules. So that is correct. Alright, so let's see. Somehow this doesn't look right. Oh, right, because I have to use double $sign to allow multiple lines, I think. So let's try that. Yep, that looks a little bit better. It still looks kind of weird because it's center aligned. Okay. Yeah. Okay, so I mean, the one extra step that I should take, at this point, is really just to kind of add up all of this stuff here, do this calculation over here, perform the actual multiplication, and then figure out what the answer is supposed to be. So I am going to finish this because it doesn't make sense to kind of just leave this one last part out. Yeah, that just doesn't make sense. And of course I have to start my spreadsheet. Alright, so I'm just using the spreadsheet here to enter the equation. It is 1 plus 0.25 plus 0.125 plus 0.0625, and then multiplied by 2 to the power of 1024 plus 64 plus 16 plus 4 minus 1023, and this is the value. So I'm gonna copy and paste it over here. Alright. So, do we have any questions about this one? So this particular question number 3, is really asking, can you identify the various parts of a double precision floating point number? And do you know how to utilize each part of a double precision floating point number? Then someone's going to ask, but Tech, why don't you just give us a value so that and ask us to convert it into the binary representation of a double precision floating point number? The answer to that question is really easy, because there's a web tool to do that for you. In other words, I cannot see whether you understand the process or not. So that's why I make a I use a made-up format that uses the same concepts. It's just that the width of the various components are different, and the bias amount is also different. So that should answer some of the questions that some people may have in their minds. My face cam is blocking. That's right. Let's turn that off. So now I can make faces all I want. Yep. Alright, so that concludes the explanation of the entire exam. Oh, you mean in Joplin? Yeah, sure. Let me export it from Joplin. Export. Okay. There has to be a way to export just one HTML file. So let me look under Note. Nope. Absolutely. Let me figure out how to export just one single note, because I know how to export the entire notebook and not just one note, but I think it's the one note that is important to you guys. Let's see. Okay. Well, one thing you guys can do is to try to do it on your own first, and then compare your answer to my answers. I mean, even though I explained the whole thing, I doubt anyone in this class can actually remember all the details that I used in today's lecture. So you can go ahead and do it on your own first, and then compare your answers to my answers. So this is for question number 1. Alright, so I think the lecture portion is done, and since I did not go over anything related to the processor, so I can't really give you the next lab assignment. So there's that. But I can use the rest of today's lab time to answer questions related to the practice exam, but I can do that after I turn off my screen share and live stream. But I will keep those on until I'm confirmed that no one else has any questions that I should address to the entire class. Okay, I don't see any specific questions in the text channel. Alright, so I'm gonna... Okay, here comes one. Oh, okay. Alright. And Ivan is still typing. I'm gonna wait until Ivan is done typing before I stop the streaming. No, I'm not taking roll today. People who missed today's lecture, I mean, yeah. No, I did not set up to take roll today. Alrighty. What kind of circuit should we be prepared for exam question number 1? Well, any type of those circuits that has a feedback mechanism. So that would be in the module, I think it's called SR Latch and Other Memory Devices, or Simple Memory Devices. I cannot remember the name of the module, but there was one module that talks about the D flip-flops, the edge-sensitive D flip-flop, the edge-sensitive and gated D flip-flop, and so on. So that would be the module to read. Right. Let's see what else is here. What kind of... Okay, are we going over anything exam related on Tuesday, or are we moving on to the next topic? Unless you guys have any questions you want to bring up on next Tuesday, it'll be moving on to more topics of the processor. And Jonathan W is correct. We have SR latch, D flip-flop, and then D flip-flops. Okay, there are multiple D flip-flops. We got the level sensitive D flip-flop, we got the edge sensitive D flip-flop, we got the edge sensitive and gated D flip-flop, and then the one after that, which is resettable, that one, it's not going to be as important. But I mean, one thing you can do is to look at this picture and figure out which flip-flop are we talking about, right? Because I didn't tell you which one it is, but by the behavior and also the design of this circuit here, it is one of those D flip-flops, just presented differently in here. Alright, and next question. So no mux D mux stuff in Q1. Yep, exactly. Matt is right. There's Q2. Q2 is all about the multiplexers and demultiplexers, the registers, the ALU, and so on and so forth. So the idea is really understand how the processor works. And I have shown quite a few instructions of how to trace and track down how the components are connected because of the tunnels. And that really is the basis of to that's what you need to understand to answer question number 2, and also how to utilize the opcode table, what each column is representing in the opcode table, um, and basically how I document how a specific operation is performed in column C, to be more exact, because column C is the one that will specify, oh, because of all the multiplexers and demultiplexers and decoder, this is now connected to that one because of and in this particular way. So that's what you need to understand for question number 2. For question number 3, it is double precision floating point number stuff, and the link that was posted earlier by Matt is the correct link. It is a Wikipedia link, but you have to understand the concepts. You have to understand what is a biased exponent of 2, why we only store the fractional part of the mantissa, right? And how we convert the value into a double, and how we convert the double back into the value that is representing. So all of that stuff is the concept that you have to fully understand in order to answer the questions. All right, so it looks like there are no further questions. I am going to